Hello everyone. Let's start a new questions about Blick script theory for the design of weir over a previous foundations. Blick script theory uh, in 1910 W.G. Bligh present a theory for subsurface flow. For what? A subsurface flow in his book entitled with Practical Design of Irrigation Works. This theory is known as a Blick script theory. First, there are some assumptions. First, according to Blick's, in a pervious foundations, where there is a foundation which is a pervious, the water percolates along the base profile of the structure, which is in contact with the subsoil. The length of the seepage path travels by the water is called a creep length. So the length that is traveled, if this is a foundation, the pervious foundation, this is the height of the dam, and this is a layer for the foundation, then the water traveling length, the seepage length or water seepage path that travels up to the length which is called as a creep length. Okay, this is a hydraulic gradient line for the floor without a vertical cutoff. If we provide a vertical cutoff in a Blick's theory, then what happens? Let's see. Bliggs made no distinctions between the creep in the horizontal directions below the floor and the creep in the vertical direction along the faces of the piles. Further, according to Bliggs, the subsoil hydraulic gradient, which is a loss of head per unit length of creep, is constant throughout the seepage path. If length L is a total creep length and H is a total head loss, if total L is a total creep length and capital H is a total head loss, the loss of a head per unit length is H by L. Figure shows a structure with a horizontal floor of length L subjected to seepage head H. For structure without sheet piles, creep length L is equal to capital L is equal to small l. For the structure with the sheet piles at upstream side and downstream side, the total creep length is L is equal to 2d1 plus L plus 2d2 d2. Let C is equal to total loss of head per unit length of the creep. C is equal to H by L. Capital H by L. H is a total head loss and L is a total length. So C is equal to H by, if we put the value of L, 2L plus L plus 2 D2. Blick's called the loss of head per unit creep length as a percolation coefficient. So this is called as a percolation coefficient. The reciprocal of this is L by H, is called the coefficient of creep. If it's a reciprocal of L by H, then it's called as a coefficient of creep. Reciprocal of total length divided by total head loss. If it's a total head loss per creep length, then it's a percolation coefficient. Following are the recommendation by Blick's theory for different types of soils like light and sand and mud, as in river Nile. Value of C, capital C, which is the coefficient of creep, is equal to 1 by C, which is 18. Value of C is 18. Find Macacaceous sands in northern Indian rivers. It's a value of C is a 15. Coarse grain soil sand for central and southern Indian, it's a 12. And boulders or gravels and sand mix, it's a 5 to 9 for value of C. There are some design criteria. Safety against piping. First, there are the two kind of safety we have to provide if we going through a Blick's theory. First is a safety against piping and second is a safety against uplift. The length of the creep should be sufficient to provide a safe hydraulic gradient H by L according to the types of the soil. There are, we had been seeing the different types of soil and value of the C. Thus, the safe creep length is given by L is equal to C into H. H by L is less than equal to 1 by C. This is no danger of piping. If this condition happens, then there is a no danger of piping. So there is no effect of piping. C is the coefficient of creep is equal to 1 by C. Now second is a safety against uplift pressures. The coordinates of the subsoil hydraulic gradient line above the bottom of the floor at any point represent the uplift pressure at the point. Let's H be the uplift pressure head at the point upon the apron. The apply pressure is W into H dash. T is equal to thickness of the floor at the point, and G is the specific gravity for the floor material, and small w is the specific weight of the water, where downward force per unit area is a W into G into T. For equilibrium, apply pressure must be equal to the weight of the floor. So if we equilibrium the conditions, so we have the it will be equal to the weight of the floor. So what is the weight of the floor? W into H dash is equal to W into G into T. So if we put T as a if we find T is equal to H by G, then we will find W both W and W will be uh, cut it out from both sides. So T is equal to H by G. So H dash is equal to G into T, where G is the specific gravity and T is the thickness of the floor. Remember that. Deducted T from both sides. If we deduct both sides, T minus T minus T, H dash minus T is equal to T G minus 1. So T is equal to H dash minus T by G minus 1 is equal to H by G minus 1, where H is coordinate of hydraulic gradient line measured above the top of the floor. Provided a factor of safety of 4 by 3, we have T is equal to 4 by 3 H by G minus 1. So effect of the floor of shifting of floor in this figure gives the floor thickness T. There is a floor thickness T at a point on apron where apply pressure coordinates measured above the top of the floor is H. If it may be noted that on the upstream side of the barrier, vice versa, weir wall or the barrage, barrier भी हो सकता है, weir wall भी हो सकती है, barrage भी हो सकता है, which upholds the water and creates the seepage head. If there is something that creates the seepage head and apply pressure are counterbalanced by the weight of the water standing on the floor. However, when there is a no water on the upstream side, if there is a no water upstream side, if this is upstream side, we call this is a upstream side and this is a downstream side of this. If there is a However, there is a no water on upstream side of the barrier, there will be no seepage head and no apply pressure. यहीं पे पानी ही नहीं होगा, तो पानी नहीं होगा तो यहाँ पे कोई सीपेज भी नहीं होगा और कोई अप्लाई प्रेशर भी नहीं होगा. इफ समझ लो यहाँ पे कोई एक बैरियर लगा दिया है, जैसे कि एक डैम है अपना, वियर है, बैरेज भी हो सकता है, तो कुछ भी है यहाँ पे, तो इसकी वजह से यहाँ पे जो भी पानी होगा उसकी वजह से एक सीपेज हेड क्रिएट होगा. अब जो सीपेज हेड है क्रिएट होगा तब उसकी वजह से अपस्ट्रीम उसकी वजह से अपने प्रेशर भी क्रिएट होगा और सीपेज भी क्रिएट होगा. एज सच फॉर एन अपस्ट्रीम फ्लोर ओनली अ नॉमिनल थिकनेस नीड टू बी प्रोवाइडेड. सो फॉर दैट प्रेशर कम होगा तो अपस्ट्रीम फ्लोर पे हम जो थिकनेस होगी फ्लोर की वो हम नॉमिनल रखेंगे. इम्पैक्ट ऑफ द फ्लोइंग वाटर और डेवलपमेंट ऑफ क्रैक्स. The floor on the downstream side of the barrier must be designed for thickness T, explained above. As the upstream floor needs to be provided with only a nominal thickness, while downstream floor has to be designed to resist apply pressure and is therefore thicker, it would be economical to provide as much as of total creep length of the upstream of the barrier as possible. However, minimum floor length will be floor length will be provided here. Okay, so this is all about the Bligh's theory. We have been seen design criteria. We have been seen shifting of the floor due to Bligh's theory. What is his considerations? So go through this and perform well. Thank you.